One of the toughest problems to solve is the reusable heat shield.
When a spacecraft comes screaming back from space, it relies on one critical component to survive: the heat shield. Building something that can withstand temperatures of thousands of degrees is already an incredible engineering challenge. But of course, SpaceX looked at that and said, what if we take one step further?
So no one has ever developed a truly reusable orbital heat shield. So it's extremely difficult to do so.
Today, we're going to dive into how SpaceX tackled the problems that haunted NASA's heat shields for decades, and how they're trying to achieve something that's never been done before: a truly reusable orbital heat shield.
So this will be the first time that it's done, that a reusable orbital heat shield is developed.
Okay, to really understand how SpaceX reinvented rocket heat shields, I think it's only fair to first look at what came before them. Because, believe it or not, engineers have been losing sleep over this problem since the very beginning of the space age. Scientists understood the reentry problem before a single human had even been launched into orbit. They knew the physics were absolutely unforgiving. When a spacecraft comes screaming back from orbit, it's traveling at around 17,500 miles per hour, or roughly 28,000 kilometers per hour. At that speed, it isn't friction that's cooking the spacecraft, it's the air itself. The atmosphere gets compressed so violently in front of the vehicle that temperatures climb above 3,000 degrees Fahrenheit, or 1,650 degrees Celsius. That's hot enough to melt aluminum, soften steel, and even rip electrons off atoms, turning the air into a glowing cloud of plasma. Basically, your spacecraft is flying through something that looks like the world's angriest lava lamp. Without a heat shield, well, you don't have a spacecraft anymore. The earliest space capsules like Mercury, Gemini, Apollo, and even the Soviet Zond program solved this problem in a surprisingly simple way. They accepted that the heat shield was going to die. These vehicles used what's called an ablative heat shield. Instead of trying to survive the heat forever, the shield slowly sacrificed itself during re-entry. The outer layers would char, melt, crack, and vaporize. And as they disappeared, they carried enormous amounts of heat away from the spacecraft. On top of that, the gases released by the burning material created a protective blanket between the vehicle and the superheated plasma. It's kind of like throwing ice cubes into a fire. Not because the ice survives, but because it absorbs a huge amount of heat while disappearing. Apollo took this idea even further by using a material called avcoat. Since astronauts were returning from the moon instead of low Earth orbit, they slammed into Earth's atmosphere at nearly 25,000 miles per hour. So the heat shield had to survive an even more ridiculous amount of heat, and avcoat did exactly that. The thing is, even this was still basically a one-time use item. Once it had burned away, that was it. You threw it out and built a brand new one. Back in the 1960s, nobody really cared. Every spacecraft was designed to fly exactly once anyway. But if humanity ever wanted space travel to become as routine as boarding an airplane, constantly rebuilding giant chunks of the spacecraft after every flight wasn't exactly a winning business strategy. So NASA came up with a completely different approach for the space shuttle. Instead of letting the heat shield burn away, why not build one that barely heated the spacecraft in the first place? The shuttle was covered with insulating ceramic tiles made mostly from silica fibers. In fact, each tile was about 94% air, which sounds like the world's worst building material, until you remember that trapped air is actually an excellent insulator. The tiles absorbed very little heat themselves. Instead, they slowed the heat so effectively that the shuttle's aluminum frame underneath stayed cool enough to survive. Their outer coating also reflected around 90% of the incoming thermal radiation, while most of the remaining heat stayed trapped inside the tile instead of reaching the spacecraft. NASA loved showing this off. After heating a tile until it glowed bright red, someone could pick it up with their bare hands just seconds later because the opposite side was still cool enough to touch. It looked like a magic trick, except the magician had a PhD in materials science. Unfortunately, the shuttle's heat shield had one enormous catch. Actually, about 24,000 catches. Because the shuttle had such a complicated shape, it needed roughly 24,000 individual ceramic tiles, and almost every single one had a unique size and shape. So if one tile got damaged, engineers couldn't just grab a spare off the shelf. They had to find the exact replacement made specifically for that exact spot. And these tiles were about as delicate as your phone screen after you've confidently said, "I don't need a case." They could crack, chip, or even fall off during launch and landing. So after every mission, technicians spent weeks, and sometimes months, carefully inspecting thousands of tiles, repairing damaged ones, and replacing others one by one. The dream of flying the shuttle every couple of weeks quickly disappeared because maintenance took far too long. So, how is SpaceX planning to solve problems that haunted NASA for decades? Well, the first thing they did wasn't invent some magical new heat shield material. They simply looked at everything that made the space shuttle difficult to maintain and tried not to repeat those mistakes. Sometimes engineering isn't about being smarter. It's about learning from the poor guy who already made the expensive mistake. Take the shuttle's launch configuration, for example. The orbiter was mounted to the side of a giant external fuel tank. During launch, chunks of foam insulation, or even ice, could break loose from the tank and slam directly into the shuttle's underside, which just happened to be where its heat shield lived. That's a bit like driving down the highway while someone in the truck next to you keeps throwing bricks at your windshield. In hindsight, putting the shuttle on top of the tank would have greatly reduced that risk, but by then, the design was already locked in. Starship completely avoids this problem. Instead of riding beside its fuel tanks, it sits on top of its super heavy booster. That means anything falling off the booster has to fight gravity before it can hit Starship's belly. Physics is finally working with the engineers instead of against them. The shape of the vehicle also makes life much easier. Unlike the shuttle's awkward winged design, Starship is basically a giant stainless steel cylinder with a pointed nose. That simple shape means most of its heat shield can be covered with identical hexagonal tiles, each about the size of a dinner plate, roughly 30 centimeters or 12 inches across. That might not sound exciting, but it's a massive improvement, making them far easier to manufacture, install, and replace. Then there's the material of the ship itself. The space shuttle's frame was made from aluminum, which expands and contracts quite a bit as temperatures change. Every flight caused the structure to flex, putting extra stress on the tiles and making them harder to keep attached. Starship uses stainless steel instead. Steel expands much less than aluminum and can survive much higher temperatures without losing its strength. That means the structure underneath doesn't have to stay nearly as cool, giving engineers a much larger safety margin. The tiles themselves are attached in a much simpler way, too. The shuttle relied on an incredibly complicated stack of adhesives, strain isolation pads, spacers, support materials, and finally, the ceramic tile itself. It worked, but it also created thousands of opportunities for something to go wrong. Starship takes a far more straightforward approach. Metal pins are welded directly onto the steel hull, and each tile has small metal clips hidden inside holes on its back that simply snap onto those pins. It's closer to snapping Lego pieces onto a base plate than carefully gluing fragile ceramic blocks onto an airplane. Well, incredibly expensive Lego pieces. Even better, the mounting system is designed to let each tile move just a tiny bit. The mounting holes have a small amount of clearance, allowing the tiles to shift slightly as the stainless steel expands, contracts, or flexes during launch, re-entry, and landing. Instead of fighting the vehicle's movement, the tiles move with it, reducing stress and eliminating the need for the shuttle's thick fabric isolation pads. However, there are still some tricky parts that need to be addressed when installing Starship's heat shield. They have to be close enough together that superheated plasma can't easily squeeze through the gaps during re-entry. But they also need enough space to avoid crashing into each other as the vehicle flexes and expands. It's one of those engineering problems where being off by just a few millimeters can suddenly become a very expensive lesson. As for the tiles themselves, SpaceX didn't start from scratch. The company already had experience developing Pika-X, an upgraded version of NASA's Pika, or phenolic impregnated carbon ablator, which protects Dragon capsules during re-entry. For Starship, however, engineers explored different high-temperature ceramic technologies, including ideas inspired by NASA's Tufrock, a material specifically designed to survive extremely harsh heating while remaining reusable. Beneath every tile sits a thin blanket of ceramic wool, most likely made from silica or alumina fibers. This insulation can tolerate temperatures of around 1,000 degrees Celsius, but it's only there as a backup. It isn't meant to save the spacecraft if a tile falls off. If that happens, the exposed steel would still experience dangerously high heating. And although most of Starship is covered with identical hexagonal tiles, there are still exceptions. The nose cone gradually narrows toward its tip, so the rows of tiles become progressively smaller. The large flaps also need many specially shaped tiles because of their curved, constantly moving surfaces. And perhaps the biggest surprise is that only about half of Starship actually has a heat shield. During reentry, Starship performs what's called a belly flop, keeping its underside pointed directly into the airflow. That's where almost all of the extreme heating occurs. The upper side mainly receives heat radiated from the surrounding plasma instead of taking the full force of the airflow. Fortunately, stainless steel is actually very good at reflecting thermal radiation, so the upper surface doesn't need ceramic tiles at all. It's the same basic idea NASA used on the space shuttle. The shuttle's underside was covered with black tiles because black surfaces radiate heat away efficiently, helping the vehicle cool down. Its upper surface was white to reflect as much incoming heat as possible. Starship follows the same philosophy, just with different materials. The black-tiled belly takes the punishment, while the shiny stainless steel upper side reflects much of the heat, saving both weight and thousands of unnecessary tiles. So, after all of those clever design changes, did SpaceX finally build the perfect reusable heat shield? Well, not quite. The good news is that Starship's heat shield is already incredibly capable. The bad news is that capable and rapidly reusable are two very different things. SpaceX doesn't just want Starship to survive reentry, they want it to land, get checked over, refueled, and fly again with as little maintenance as possible. That's an insanely high bar, and they're still working toward it.
The heat shield, it is an achievable thing, so we're not trying to do something that isn't achievable. It is within the realm of physics to get this done, just an extraordinarily difficult thing to get done.
Fortunately, this is where SpaceX's favorite engineering strategy comes in. Fly it, break it, figure out why it broke, then build a better version. Repeat until it works. That's exactly how Starship's thermal protection system has evolved. During the first orbital flight tests, from IFT-1 through roughly IFT-4 in 2023 and early 2024, Starship was covered with nearly 18,000 black hexagonal ceramic tiles. They looked impressive, but the flights quickly exposed several weak points. Some tiles simply fell off, others cracked. And in some places, the tiles stayed attached just fine, but superheated plasma squeezed through the tiny gaps between them and scorched the stainless steel hull underneath. After the lessons learned from Flight 4, the vehicle known as Ship 30 underwent a massive overhaul before Flight 5. SpaceX removed and replaced the vast majority of the entire heat shield. The new ceramic tiles were reportedly about twice as strong as the previous generation, making them much more resistant to cracking and damage during launch and re-entry. But perhaps the most important addition wasn't the tiles themselves, it was what went underneath them. Earlier Starships relied mostly on thermal blankets beneath the ceramic tiles. Ship 30 introduced a secondary ablative layer, a black protective sheet installed over the mounting pins before the tiles were attached. Think of it as a backup shield for your shield. If a ceramic tile were damaged or ripped away during flight, this layer could temporarily burn away, just like the ablative heat shields used on Apollo and Dragon, protecting the stainless steel hull long enough to survive the hottest part of re-entry. It's not meant to replace the ceramic tiles, but it gives Starship a much better chance if something goes wrong. SpaceX also continued improving the mounting pins, adhesives, and attachment hardware, while giving extra attention to the flaps, since those moving surfaces experience some of the harshest aerodynamic loads during re-entry. And then came the 2025 test flights, where things started looking much better. By Flight 10, Starship achieved something that would have seemed almost impossible during the early tests. Nearly every heat shield tile stayed attached throughout the mission. That's a huge milestone. Because at this point, SpaceX wasn't just trying to stop tiles from falling off anymore, they were intentionally making the vehicle harder to protect. Seriously, engineers deliberately removed a handful of ceramic tiles before launch to study how the vehicle behaved with missing protection. They also installed several experimental metallic heat shield tiles alongside the normal ceramic ones. The idea sounded promising. Metal tiles would be simpler to manufacture, tougher against impacts, and potentially easier to maintain than fragile ceramics. Reality, however, had other opinions. During reentry, the metallic tiles oxidized heavily, turning orange and reddish-brown, and they simply didn't perform as well as the ceramic versions. The experiment still provided valuable data, but for now, ceramic tiles remain the better choice. Flight 10 also revealed another clever upgrade that solves one of Starship's most stubborn problems. Remember those tiny gaps between the tiles? They're unavoidable. The stainless steel structure expands and contracts as it heats up and cools down, so the tiles need a little room to move. If they were packed tightly together, they'd simply crash into each other and crack. But leaving gaps created another problem. Plasma could squeeze through them during reentry and overheat the structure underneath. SpaceX's solution is something engineers have nicknamed the crunch wrap.
However, that lets some of that plasma kind of seep through, and we see really high heating on the sides and then down on the metal. To help fix that, we have this, the crunch wrap that everyone has heard about. So we take essentially that's called Vulcan felt that we then wrap around. And so as these tiles are next to each other, you've got a small bit in between that's going to help offset that heating.
Then came the next major leap, Starship V3. One of the biggest highlights of Flight 12, the very first V3 flight, wasn't actually the launch itself. It was what happened after the mission, when Starship came screaming back through Earth's atmosphere. As the vehicle descended, performed its dramatic flip maneuver, and lit its engines for the landing burn, engineers got their first really good look at the condition of the heat shield. And honestly, it looked surprisingly good. Compared to the rough-looking heat shields seen on several V2 flights, this one appeared remarkably clean, uniform, and almost completely intact. Instead of obvious missing sections and heavily damaged areas, the tiles stayed in place across most of the vehicle, suggesting far better tile retention and much more even thermal protection during re-entry. There are almost certainly more improvements coming. SpaceX has never been the type of company to look at something that works and say, "Yep, that's good enough." But Flight 12 showed something that's arguably even more important than perfection. It showed steady progress. Compared to where the program started just a couple of years ago, the progress has been remarkable. Every successful re-entry gives SpaceX another mountain of data, and every mountain of data gets them one step closer to a heat shield that can survive the trip to space. And do it again the next day. Starship can't land on the moon. At least not yet. Before it can, it has to solve a surprisingly important problem: not falling over. And to do that, SpaceX may need to bring back something it's been trying to avoid for years: landing legs. So today we're going to look at how SpaceX could put legs back on Starship and the science behind keeping a 50-meter-tall rocket standing upright on the moon. We'll also see why landing legs are only the first step. Getting Starship safely onto the lunar surface is one challenge. Turning it into a vehicle that can actually support astronauts is another. This is the story of how Starship could become a true moon lander. The basic physics is actually pretty simple. Think about standing upright. If your feet are close together, someone can push you over fairly easily. Spread your feet wider apart, and suddenly you're much harder to knock over. You're creating a larger support footprint. Starship follows exactly the same rule. When engineers talk about landing stability, three things matter most. How far are the landing feet from the vehicle's centerline? How high is the center of gravity? How many landing legs are there? But unfortunately for SpaceX, Starship HLS starts with a disadvantage. It's enormous. At roughly 50 meters tall, Starship is less like a traditional lunar lander and more like trying to park a small skyscraper on the moon. Even if most of the propellant has been burned off before landing, the vehicle still has a relatively high center of gravity compared to something like Apollo's lunar module. That's why some engineers and space enthusiasts have raised eyebrows at several of SpaceX's early renderings. In some illustrations, the landing legs appear surprisingly short compared to the height of the vehicle. If the feet are only a few meters away from the center line, the stability margin becomes smaller. Suddenly, things like slopes, rocks, uneven terrain, or a slightly off nominal landing start becoming much more important. So how do you improve stability? Of course, the obvious solution is just make the legs bigger. A wider stance means the vehicle can tolerate steeper slopes, larger rocks, and greater differences in terrain height before it reaches the point where gravity starts trying to pull it over. Imagine balancing a broom upright. The farther apart your feet are, the easier it is to keep that broom standing. This thinking is great until physics shows up and starts charging extra fees. Longer legs mean more mass, more structural loads, more complicated deployment systems, and ultimately more weight that has to be launched all the way to the moon. Space engineers hate unnecessary mass almost as much as airline passengers hate baggage fees. So how does SpaceX decide how wide the legs need to be? First, they determine the vehicle's mass, center of gravity, expected landing conditions, and the maximum tilt angle they can safely tolerate. Then they feed all of that into computer simulations. Lots of simulations. What happens if one foot lands 50 centimeters higher than the others? What if the surface slopes by 10 degrees? What if a leg sinks into soft lunar regolith? Engineers can simulate thousands or even millions of these scenarios until they find a design that survives nearly all of them. Then there's the boulder problem. The moon is basically a giant rock collection with occasional scenery. A landing site might look perfectly flat from orbit, but a foot could still end up on a hidden rock. Maybe the rock crushes. Maybe it sinks into the soil. Maybe nothing happens at all. Or maybe it shifts after touchdown, and suddenly your lunar lander starts impersonating the Leaning Tower of Pisa.
That's why modern lunar landers don't rely solely on strong landing legs and crossed fingers. Long before the spacecraft touches the surface, it's already searching for the safest place to land, using high-resolution orbital imagery, radar, LiDAR, and increasingly sophisticated hazard detection software. For decades, radar was the go-to tool for measuring altitude and descent speed. It works well, but it has limitations. Radio waves spread out over a fairly large area, which means small craters, rocks, and other hazards can sometimes hide within the radar's field of view. That's a bit like trying to inspect a parking space through a foggy windshield. You'll spot the big obstacles, but the smaller ones might surprise you at the worst possible moment. Radar also struggles with a particularly annoying problem: separating changes in altitude from changes in velocity. Imagine flying over the edge of a steep crater. Your distance from the ground changes rapidly, but your actual speed may not. If a guidance system interprets that sudden range change as a velocity change, it could react in ways that are, let's just say, undesirable for a lunar landing. That's where LiDAR comes in. LiDAR, short for light detection and ranging, works on the same basic principle as radar, except it uses laser light instead of radio waves. It sends out pulses of visible or infrared light and measures how long they take to bounce back. By analyzing the returning signal, including tiny Doppler shifts, LiDAR can measure both distance and velocity directly and with remarkable precision. The biggest advantage is that lasers produce an incredibly narrow beam. Instead of illuminating a broad patch of terrain, LiDAR can examine specific features with much greater accuracy. It's the difference between lighting up a football field with a floodlight and pointing a laser pointer at a single rock. For a vehicle as tall as Starship, that level of precision could be invaluable. The moon is covered in slopes, craters, and enough rocks to keep a geologist entertained for several lifetimes. Finding a safe landing spot is a requirement. This is why Starship will likely rely on a combination of advanced sensors, hazard avoidance software, extremely careful landing site selection, and possibly wider or self-leveling landing legs. There's also an even more interesting idea floating around: self-leveling landing legs. SpaceX has discussed concepts where the legs wouldn't just unfold and hope for the best. After touchdown, each leg could adjust itself independently, some compressing more, others retracting slightly, to compensate for uneven terrain. Think of it as the lunar version of an off-road truck's suspension. Your average pickup can handle a rocky trail because the wheels move independently. Starship would be trying to do something similar, except instead of carrying camping gear, it's carrying astronauts and several hundred tons of spacecraft. No pressure. The big advantage is obvious. The lander wouldn't need a perfectly flat parking spot. If one foot lands on a small rise and another lands in a shallow depression, the legs could adjust and level the vehicle instead of leaving it tilted like a wobbly restaurant table. For a spacecraft as tall as Starship, that capability could be incredibly valuable.
It could tolerate much larger variations in surface height without requiring absurdly long landing legs or a lunar surface that's been pre-approved by a team of obsessive landscape architects. At the moment, SpaceX hasn't publicly revealed the final HLS landing leg design, but whatever solution they choose, it will have to solve a very unusual challenge. Not just landing the largest lunar spacecraft ever built, but keeping it standing afterward. Now, being able to land upright is only the first challenge. Starship HLS still needs a long list of upgrades before it can comfortably deliver astronauts to the lunar surface. One of the most obvious questions is, once Starship lands, how do the astronauts actually get down? Remember, this thing is roughly the height of a 15-story building. The crew cabins and airlock aren't near the ground, they're located high up inside the vehicle. After landing, astronauts need a reliable way to reach the surface for moonwalks, scientific work, and moving cargo. So SpaceX came up with a practical solution: an elevator. Yes, Starship HLS literally includes a lunar elevator. The system uses a platform, or basket, that travels along rails mounted on the outside of the spacecraft. Astronauts step onto the platform near the airlock, ride it down to the surface, and then use a deployable ramp to walk onto the moon. The same system can also transport tools, scientific equipment, and cargo. In many ways, it's less like a traditional spacecraft system and more like installing an industrial freight elevator on the side of a rocket. Of course, building an elevator for the moon is a little more complicated than installing one in an office building. The mechanism has to operate in extreme temperatures, vacuum conditions, and lunar dust. And lunar dust is notorious for getting into everything. Moon dust makes beach sand look cooperative. To help refine the design, NASA astronauts tested elevator mock-ups at SpaceX's Hawthorne facility. Wearing pressurized spacesuit analogs, they evaluated controls, gate operations, ramp deployment, cargo handling, and overall usability. The goal was to identify problems on Earth before astronauts encounter them 384,000 kilometers away. However, the elevator has attracted some criticism. A NASA Office of Inspector General report noted that the current design lacks an alternative method for astronauts to enter or exit the vehicle if the elevator fails. In engineering terms, that makes it a potential single point of failure, one component whose failure could seriously affect the mission. But what exactly is the backup supposed to be? A giant emergency ladder stretching down the side of a 50-meter spacecraft doesn't sound particularly appealing. Climbing that distance in a bulky moon suit would be challenging even under ideal conditions, and lunar gravity doesn't magically make ladders fun. So while NASA's concern is understandable, the practical solution probably isn't a ladder. The real answer is likely making the elevator so reliable that its chances of failure become extraordinarily small. Multiple motors, redundant power systems, backup controls, fault-tolerant software. Because when your lunar exploration program depends on an elevator, out of order becomes a phrase nobody wants to see. Some other major upgrades include the docking system located near the front of the vehicle. This port is specifically designed to work with NASA's Orion spacecraft, allowing astronauts to transfer safely between the two vehicles while orbiting the moon. The hardware itself is based on the docking mechanism SpaceX already uses on Dragon missions, which is good news because using something that's already flown successfully tends to make NASA engineers sleep better at night. The system can operate in multiple docking modes and was put through extensive ground testing, including hundreds of simulated docking scenarios involving different approach speeds and angles. Because if two spacecraft are going to meet hundreds of thousands of kilometers from Earth, you really want to be sure they can shake hands properly. Starship HLS also carries a set of specialized reaction control thrusters mounted around the middle of the vehicle. These methane and oxygen-powered thrusters provide the precise steering needed during the final stages of lunar descent. Think of them as the spacecraft's fine control system, making tiny adjustments while the main engines handle the heavy lifting. Inside, the vehicle needs to function as a temporary home for astronauts. That means providing oxygen, environmental control, temperature regulation, and waste management systems capable of supporting the crew throughout the mission. In many ways, Starship HLS isn't just a lunar lander, it's also a small space station that happens to land on the moon. Radiation protection is another major consideration. Unlike astronauts in low Earth orbit, lunar crews spend much more time exposed to deep space radiation. The HLS design incorporates shielding through its structure, materials, and internal layout to keep astronaut exposure within NASA's safety requirements. Interestingly, one of the biggest changes is what Starship HLS doesn't have. Since it never returns to Earth, it doesn't need the thousands of heat shield tiles or the giant aerodynamic flaps found on standard starships. Those systems are essential for surviving a fiery re-entry through Earth's atmosphere, but they're just dead weight on a lunar mission. Removing them saves mass and simplifies the vehicle, while the stainless steel structure still provides the strength needed for space operations. Then there's the propellant problem. Unlike a normal spacecraft that spends a few days in orbit, Starship HLS may need to store enormous quantities of supercold methane and liquid oxygen for extended periods. Keeping those propellants from slowly boiling away is one of the biggest engineering challenges facing the entire program. To combat this, SpaceX uses advanced insulation, specialized tank designs, and common bulkhead structures to reduce heat leakage into the propellant tanks. Ground testing has shown promising results, but the real test will come in orbit, where months-long operations in microgravity introduce challenges that are difficult to fully reproduce on Earth. The goal is to preserve roughly 1,200 tons of propellant after orbital refueling so that enough remains for lunar landing, surface operations, and the return trip to lunar orbit. So now that we've got a pretty good idea of what Starship HLS looks like and all the upgrades needed to turn it into a lunar lander, there's only one thing left to do: actually land on the moon. The mission begins long before the astronauts leave Earth. First, a specialized Starship HLS launches into orbit aboard a super heavy booster. Unlike a normal moon mission, this vehicle can't head directly to the moon because it needs a truly ridiculous amount of propellant. So after reaching orbit, it waits while multiple Starship tanker flights rendezvous and refill its tanks. Current estimates vary, but the mission could require anywhere from several to more than 10 tanker launches, depending on future optimizations. Once fully fueled, Starship HLS performs a burn toward the moon and enters a near-rectilinear halo orbit, or NRHO. Think of it as a giant parking orbit around the moon where the lander waits for its passengers to arrive. Next comes NASA's part. 4 astronauts launch aboard Orion on top of the Space Launch System from Kennedy Space Center. Orion travels to the moon and rendezvouses with the waiting Starship. After docking, 2 astronauts transfer into Starship HLS while the other 2 remain aboard Orion. At this point, the lunar lander and its crew separate from the command vehicle and begin their descent toward the lunar South Pole. Starship is expected to perform most of the landing autonomously. Advanced sensors, cameras, radar, LiDAR, and onboard computers continuously analyze the terrain and guide the vehicle toward a safe landing site. However, NASA's Office of Inspector General has raised concerns about the current level of crew control available during landing. NASA traditionally prefers astronauts to have the ability to manually intervene if automation encounters unexpected problems. To be fair, manually flying Starship onto the moon isn't quite the same as landing an Apollo lunar module. Apollo astronauts could look out the window and directly judge the terrain below. Starship is a 50-meter-tall spacecraft with the crew compartment located near the top. Trying to manually land it by eyesight alone would be a bit like attempting to parallel park a skyscraper while sitting on the roof. Anyway, assuming everything goes according to plan, Starship touches down near the lunar South Pole. The elevator then springs into action, carrying astronauts and equipment between the surface and the crew compartment high above. For the next 6 or 7 days, the astronauts conduct moonwalks, collect samples, deploy scientific instruments, and explore the surrounding terrain. Thanks to Starship's enormous internal volume, they'll have far more living space than any lunar crew in history. Compared to Apollo's lunar module, it's the difference between camping in a small tent and staying in a studio apartment. Eventually, it's time to head home. Starship lifts off from the lunar surface and returns to NRHO, where it rendezvouses with Orion once again. The astronauts transfer back to Orion along with their lunar samples, scientific data, and hopefully fewer moon dust particles than expected. Finally, Orion undocks and begins the long journey back to Earth. Since it's the only spacecraft in the mission designed to survive high-speed lunar re-entry, Starship stays behind while Orion plunges into Earth's atmosphere and splashes down in the Pacific Ocean. And that's the entire Artemis lunar landing sequence. Dozens of launches, orbital refueling, lunar rendezvous operations, autonomous precision landings, a giant elevator on the side of a rocket, and a week living on the moon. So, mission accomplished. Humans are back on the moon. Except that's not actually the end goal. NASA isn't spending billions of dollars and coordinating one of the most complex space missions ever attempted just so astronauts can visit for a few days, take some pictures, and head home. The real objective is much bigger, building a permanent presence on the moon. A place where people can live, work, conduct research, and eventually prepare for missions deeper into the solar system. And that's where cargo Starship enters the picture. In early 2024, NASA expanded work on a cargo version of Starship HLS to support the long-term Artemis vision. Unlike the crewed lander, this version doesn't need cabins, life support systems, sleeping quarters, or any of the hardware required to keep astronauts alive. It has one job: move enormous amounts of stuff to the moon. And when Starship is involved, enormous really means enormous. The cargo variant takes advantage of Starship's massive internal volume, roughly 1,000 cubic meters of payload space. To put that into perspective, that's less like loading a spacecraft and more like loading a small warehouse. Without having to reserve space for astronauts, the vehicle can be configured to carry habitats, power systems, scientific laboratories, construction equipment, autonomous rovers, and other infrastructure needed to transform a landing site into an actual lunar outpost. The landing system itself may also be strengthened to handle particularly heavy payloads. After all, gently setting down a crew cabin is one thing. Delivering dozens of tons of equipment designed to survive years on the moon is another. The most impressive number, however, is the projected payload capacity. SpaceX believes the cargo version could eventually deliver up to 100 metric tons of cargo to the lunar surface in a single mission. That's a staggering amount of mass. For comparison, the entire Apollo lunar module weighed only about 15 tons at launch. A single cargo Starship could potentially deliver several times that amount directly to the moon in one trip. Suddenly, ideas that once sounded like science fiction start becoming realistic. Instead of carefully packing every mission around a few hundred kilograms of equipment, planners can begin thinking about full-sized habitats, large solar farms, heavy excavation machinery, and fleets of robotic vehicles. In other words, the crewed Starship helps astronauts visit the moon. The cargo Starship helps them stay. Because history has shown that exploration is only the beginning. The first ships crossing an ocean aren't what changed the world. It's the cargo ships that follow afterward, bringing the supplies needed to build something permanent. And if Artemis succeeds, the same story may play out on the moon. SpaceX was never supposed to succeed.
And let me tell you, if people had told me this was gonna happen, I was like, man, you must be smoking some really good crack. Because I think this company's gonna fail.
One thing Elon Musk says a lot is that when he started SpaceX, he gave the company less than a 10% chance of succeeding. And honestly, that wasn't him being dramatic. If anything, 10% was probably optimistic. Today, it's easy to look at SpaceX and think, well, of course they succeeded. They launch rockets every week, land boosters like it's a routine parking maneuver, and somehow make billion-dollar spacecraft look like software updates. But back in the early 2000s, the situation looked very different. Giants like Boeing and Lockheed Martin dominated the launch industry. These companies had decades of experience, enormous government contracts, thousands of employees, and more aerospace expertise than most countries. Meanwhile, SpaceX was basically a startup operating out of warehouses. To many industry veterans, Musk didn't look like a future rocket pioneer. He looked like a guy speedrunning bankruptcy with extra steps. But the thing is, he actually had a plan that would completely reshape how a rocket company operates, challenge decades of industry assumptions, and eventually help push SpaceX to the top of the aerospace world. And today, we're going to break down exactly what that plan was. In 2001, Musk traveled to Moscow hoping to buy retired ballistic missiles and turn them into launch vehicles. Today, that sounds like the kind of plan you'd come up with at 2 a.m. after drinking way too much coffee and binge-watching rocket documentaries. But at the time, it was a completely serious proposal. The meetings reportedly involved plenty of vodka, plenty of posturing, and not much actual progress. We won't get too deep into everything that happened in those meetings, but the short version is this. The Russians didn't take Musk very seriously, and they quoted a price he thought was ridiculous, about $8 million per missile. The failed deal itself wasn't the important part, though. What mattered was what Musk realized on the flight home. He started asking a simple question: why are rockets so expensive? That question ended up changing everything. It eventually led to one of Musk's core ideas, something he later called the Idiot Index. It's a useful concept to remember because it became one of the foundations of how SpaceX operates. Musk's goal was simple: figure out why every rocket component cost what it did. Sometimes there were good reasons, sometimes there weren't. By questioning every part, every process, and every supplier, SpaceX discovered that many aerospace components carried enormous markups, not because they were impossibly difficult to make, but because the industry had been doing things the same way for decades, and nobody had seriously challenged the system. Let me explain this principle a little further, and Falcon 9 is probably the best example of it in action. When people talk about Falcon 9, they usually focus on the rocket itself, the reusable boosters, the spectacular landings, and the fact that SpaceX somehow made rocket launches feel almost routine. And to be fair, those things are impressive. But one of the most important things Falcon 9 proved wasn't about engines, fuel, or even reusability. It was about money. Back in 2010 and 2011, NASA decided to investigate a question that was making a lot of people in the aerospace industry uncomfortable. If Falcon 9 had been developed using a traditional NASA-style program instead of SpaceX's approach, how much would it have cost? The answer was a lot. Like, someone accidentally added a few extra billions to the invoice a lot. Using the NASA Air Force cost model, NASA estimated that a traditional government-led development program would have cost about $3.98 billion. A commercial development program similar to SpaceX's approach would have cost around $1.38 billion. And under a pure fixed-price commercial model, the estimate dropped all the way to about $443 million. So NASA's conclusion was pretty remarkable. Falcon 9 may have cost anywhere from 3 to 9 times less than a comparable government-run development effort. Same rocket, very different bill. The question is, how? According to SpaceX, one major reason was simply having fewer people. Rocket development is mostly salaries. No matter how advanced the technology is, every engineer, manager, analyst, and administrator needs to be paid. If one program employs 10,000 people and another employs 1,000 people, the payroll alone starts creating a massive difference in cost. SpaceX deliberately kept its teams relatively small, at least at the time. Instead of building huge chains of management where information travels through layer after layer of supervisors and review boards, they tried to keep decision-making close to the engineers actually building the hardware. Less time spent preparing presentations, more time spent making rockets. Another huge factor was vertical integration, which sounds complicated but really means build it yourself whenever possible. Traditional aerospace projects often involve a long chain of contractors. NASA hires a prime contractor. The prime contractor hires subcontractors. Those subcontractors sometimes hire even more subcontractors. Every layer adds management costs, overhead, reporting requirements, and profit margins. SpaceX argued that a component that physically costs $1 million to manufacture can end up costing $3 million, $4 million, or even $5 million once all those extra layers take their share. The part itself hasn't changed. It just collected paperwork like a snowball rolling downhill. Fewer middlemen meant fewer opportunities for costs to multiply. Infrastructure was another area where SpaceX kept things lean. Traditional aerospace programs often operate across multiple facilities, test centers, management offices, and support organizations. Maintaining all of that infrastructure costs money, whether rockets are being built or not. Think of it like owning one busy restaurant versus owning 5 half-empty restaurants. Both businesses technically serve food, but only one isn't constantly wondering how to pay for all the unused space. What NASA found particularly interesting was that the biggest difference wasn't really technical at all. It was organizational. SpaceX generally worked with relatively stable requirements, lean management structures, fixed budgets, and a culture that pushed engineers to make decisions early. Traditional government programs often operate under heavier oversight, larger management structures, annual budget cycles, and requirements that can change repeatedly throughout development. Imagine trying to build a house. One approach is deciding what house you want and then building it. The other approach is deciding halfway through construction that you'd like another floor, then scheduling 6 meetings to discuss the new floor, then creating a committee to review the meetings about the floor. The second approach might reduce certain risks, but it usually doesn't help the budget. NASA's estimates became even more interesting after agency engineers visited SpaceX facilities and inspected the actual hardware. Before the visit, NASA estimated Falcon 9's development cost at roughly $1.66 billion under a SpaceX-like approach. After seeing how the company actually operated, that estimate dropped to about $1.38 billion. The fixed price estimate fell to around $443 million. The visit revealed several things NASA hadn't fully accounted for. For one, Falcon 9 wasn't being developed entirely from scratch. NASA's original analysis treated it as a mostly new vehicle, but SpaceX had already gained significant experience from the earlier Falcon 1 program. Falcon 1 may not have become a commercial success, but it taught the company valuable lessons about engines, structures, manufacturing, testing, and launch operations. A lot of expensive mistakes had already been made once, which meant they didn't need to be paid for again. NASA also discovered that even though SpaceX built a lot of stuff in-house, they also rely more on off-the-shelf hardware than originally assumed. Not every component was custom designed. Sometimes the cheapest solution is simply buying a part that already exists and works. This sounds obvious, but aerospace has occasionally demonstrated a remarkable talent for turning simple parts into expensive science projects.
And that's where the most surprising part of the entire study appears. The rocket itself barely changed. The engines didn't change. The tanks didn't change. The physics certainly didn't change. What changed was the management structure, the oversight requirements, the contracting system, the reporting burden, and the overall size of the workforce. Falcon 9 wasn't only a demonstration of new hardware, it was a demonstration that a completely different way of developing hardware could potentially save billions of dollars. In fact, the success of Falcon 9 helped convince the agency that fixed-price partnerships could work. Instead of reimbursing companies for every dollar they spent, NASA increasingly moved toward paying companies for delivering specific results. That philosophy eventually shaped programs like Commercial Crew, where the focus shifted from tracking expenses to achieving milestones. But SpaceX's advantage isn't just cheaper manufacturing, vertical integration, or economies of scale. It's speed. More specifically, it's the speed at which decisions get made. One of the biggest differences between SpaceX and traditional aerospace organizations isn't the hardware. It's what happens when somebody walks into a meeting and says, "I think we should change this." At SpaceX, that discussion might be resolved in a few days, in some cases, even a few hours. At a large government program or traditional aerospace contractor, the same decision can bounce between teams, managers, review boards, contractors, subcontractors, and committees for months, or sometimes years. Now, to be fair, there's a reason for that. When you're building a machine that contains thousands of tons of explosive propellant and costs hundreds of millions of dollars, being careful is generally considered a good idea. Rocket science is one of the few professions where a small mistake can instantly transform years of work into a very expensive fireworks show. But SpaceX approaches the problem differently. The company operates with an enormous sense of urgency, driven by its long-term goal of making humanity a multi-planet species. Whether you agree with that goal or not, it creates a culture where moving fast is considered essential. The philosophy is often simple. Make the best decision you can with the information available. Then move. Because waiting forever for perfect information is also a decision, and often an expensive one. Ironically, NASA once operated in a very similar way. During the Apollo era, the agency was racing against the Soviet Union to reach the moon. Schedules were brutal, decisions were made quickly, and engineers were constantly pushing forward. The difference is that Apollo had a deadline. Today's programs often don't. And without a giant geopolitical clock ticking in the background, organizations naturally become more cautious.
The problem is that fast decisions sometimes turn out to be bad decisions, and bad decisions in aerospace can be spectacularly bad. A design choice might look brilliant in a conference room and completely fall apart the moment real hardware gets involved. The question isn't whether mistakes happen. They always do. The question is how quickly you can recover from them. And this is where SpaceX has another major advantage: agility. If SpaceX discovers that a design isn't working, it can often pivot remarkably quickly. A team redesigns the part. The factory builds a new version. The test team installs it, and the next prototype is already moving toward the launch pad. That's possible largely because SpaceX builds most of its hardware in-house. The engineers, manufacturing teams, and testing teams are all working under the same organizational roof. If something needs to change, they can often walk across the building and start fixing it. Compare that to a traditional aerospace program involving multiple contractors, subcontractors, suppliers, oversight organizations, and government agencies. Changing one component can sometimes feel like trying to edit a group project after 15 different people have already submitted their versions. By the time everyone agrees on the change, somebody has probably scheduled 3 more meetings about it. Of course, making decisions quickly is only half the equation. The other half is finding out whether those decisions were actually correct. And there's really only one reliable way to do that: build something and test it. Engineers can run simulations all day long. They can create models, perform calculations, and fill entire hard drives with data. But eventually, physics demands an answer. The rocket either works, or it very enthusiastically demonstrates why it doesn't. The challenge is that building hardware quickly and testing it aggressively comes with a very obvious downside. Sometimes it explodes. Actually, it tends to explode a lot. And that's exactly the trade SpaceX was willing to make. Because if your goal is to learn as quickly as possible, a failed test that teaches you something valuable can be more useful than a successful test that teaches you nothing. Which is why SpaceX became famous for a development philosophy that would make many traditional aerospace managers break out in a cold sweat. Build it, fly it, break it, fix it, then do it again. Now, the biggest breakthrough, though, was reusability. Before SpaceX, the industry mostly treated rockets like disposable paper cups. Use once, throw away. Nobody really questioned it because that's just how rockets worked. Not until Elon looked at a booster worth tens of millions of dollars and basically asked, what if we stop throwing these rockets away after every flight? That one idea changed the economics of spaceflight. When NASA analyzed Falcon 9's costs, the first stage, the booster, was by far the most expensive part of the rocket. Depending on how you calculate it, the booster represents roughly 60 to 70% of the vehicle's total value, which makes sense when you think about what is packed into that giant metal cylinder. Inside are 9 Merlin engines, each costing roughly $1 million. Then there are the massive aluminum lithium propellant tanks, the avionics systems, wiring, plumbing, hydraulic systems, carbon fiber landing legs, titanium grid fins, and thousands upon thousands of individual components that all need to work perfectly every single flight. It's basically a flying factory packed with some of the most sophisticated hardware SpaceX builds. No wonder SpaceX became obsessed with bringing boosters back. The second stage, however, is a different story. Unlike the booster, it still gets sacrificed on every mission. It reaches orbit, performs its job, and then eventually burns up in the atmosphere or remains in space, depending on the mission profile. So no matter how many times a Falcon 9 booster flies, every launch still requires a brand new upper stage. Then there are the fairings. Those 2 clamshell-shaped pieces at the tip of the rocket don't look particularly exciting. Most people probably pay more attention to the fire coming out of the engines, but the fairings are surprisingly expensive. They're aerospace-grade carbon fiber structures with aluminum honeycomb cores, acoustic protection, thermal protection systems, and carefully engineered separation mechanisms. A brand new set costs roughly $6 million. Which explains why SpaceX doesn't just let them splash into the ocean and disappear. When you realize you're throwing $6 million into the sea every launch, suddenly fishing things out of the water starts sounding like a very reasonable hobby. A dedicated Falcon 9 launch typically sells for around $70 to $75 million. Various estimates suggest the actual cost to SpaceX may be around $29 million per launch, thanks largely to booster reuse and fairing recovery. That means a single mission can potentially generate something on the order of $40 million in profit. Not bad for a rocket company that many experts expected to fail 20 years ago. Even though Falcon 9 remains SpaceX's workhorse, the company increasingly sees it as the rocket that buys time for its next best thing, Starship. Because for SpaceX, Starship isn't just another rocket. It's the vehicle that makes almost everything else possible. The latest Starship V3 is the largest and most powerful rocket ever built, taller than a 40-story building and more than twice as powerful as the Saturn V that carried astronauts to the moon.
Historically, reaching orbit cost around $18,500 per kilogram. Falcon 9 slashed that to roughly $2,700. Falcon Heavy pushed it down further to about $1,400. Starship's ultimate goal is to bring that number all the way down to somewhere between $100 and $500 per kilogram through full and rapid reusability. In other words, SpaceX isn't trying to build a slightly better rocket. It's trying to make access to space so cheap that entirely new industries become possible. At the same time, Starlink has become the company's financial engine. What started as a way to fill spare launches has grown into a global internet network with more than 10 million subscribers across 164 countries, powered by over 9,600 satellites. The business now generates billions of dollars each year, providing the cash flow needed to fund SpaceX's far more ambitious projects. Everything, from Falcon 9 to Starship to Starlink, ultimately serves the same long-term vision Elon Musk laid out years ago, building a permanent city of at least 1 million people on Mars. And because apparently that wasn't ambitious enough, SpaceX is also exploring the possibility of massive space-based data centers consuming more than 100 terawatts of power, over 1,000 times the combined power usage of every data center on Earth today. Those are enormous goals. But Musk has a long history of making predictions about SpaceX that sounded impossible at the time, only for them to eventually become reality. He said SpaceX would put humans into orbit when no private company had ever done it before. Today, the company routinely flies NASA astronauts to space. He said SpaceX would land and reuse orbital-class rockets when the rest of the industry treated boosters as disposable. Since then, Falcon 9 boosters have landed and flown hundreds of times again. He said a satellite internet business could be worth tens of billions of dollars when the industry was littered with failed satellite internet ventures. Today, Starlink has grown from zero revenue to more than $11 billion annually in just a few years. The timelines were often optimistic. The direction was almost never. And now you've learned the secret behind how SpaceX pulled it off. The company didn't achieve those milestones because it had the most money or the most experience. In fact, it had neither. It succeeded because it approached costs differently than everyone else. Instead of accepting that rockets had to be expensive, SpaceX questioned every assumption. Why does this part cost so much? Can we build it ourselves? Can we reuse it? Can we manufacture it faster? Can we simplify it? Those questions transformed SpaceX from a company that was one launch away from bankruptcy into one of the most valuable private companies on Earth.
I told people this. I said, look, we're probably going to fail, but we should give it a try, because if we don't, if there's not a new company that enters space, we will never be a truly spacefaring civilization. The other aerospace companies, they build good rockets and everything. They were simply not pursuing the technology that's necessary to make life multiplanetary, to make Star Trek, to make the exciting science futures that we've read about real. And that's what SpaceX is all about, is to take the fiction out of science.